we're going to keep talking about ways to describe distributions with numbers. This is our second day of that, and really just kind of picking up where we left off during our last class. Last class we looked at box plots, and we talked about IQR and measures of spread and 5-number summaries and things like that. So we're actually, this is the opening slide for today. We're going to talk a little bit about standard deviation today as another method for describing spread. I have some questions for you to work on towards the end of class that the guest teacher or substitute is going to give to you here in a little bit, or maybe already has. And then the homework for next class is I have a split between some homework problems, a couple homework problems, finishing up that dissolved oxygen worksheet, and then continuing making progress on that reading guide. Due Tuesday, I'll take a chapter 1 quiz on Tuesday as well, and I'll be here for the next class to go over any questions that you might have and things like that heading into Tuesday's quiz. So hopefully the sub has already passed this out to you. This is just the note set for today. And basic idea here is we're going to try to treat this as if I were in class in front of you, but we're just not going to be able to ask questions. So if you have questions at any point along the way, just jot them down on the side of your notes, and I'll handle those when I come back during our next class. Okay, so this was the data set that we started with last class, and we looked at 2 different groups of data, and what we saw there was the measures of center were actually exactly the same for both of these distributions, and so we use that as a way to just really kind of take a look and say, well, measures of center are not enough. Oftentimes we talk about the means or the medians, and that's a good measure of the middle, but there's also a story to be told for how the data is spread as well. And so we talked a little bit about that during our last class. We're going to go ahead and go down here, and we'd like for you just to take a minute to, as a review from last class, just go ahead and find the following measures of spread for both groups. Take a minute to find the range for Group A and for Group B, and then also the IQR for Group A and Group B. And just go ahead and press pause and take a minute to do that, and then when you're finished with that, go ahead and replay the video, or start it up rather, and we'll talk about the answers a little bit. Okay, so as you hopefully figured out, the range for Group A is 12, and for Group B would be 58, and also the IQR for Group A is going to be 10. The IQR for Group B is going to be 27, and we can sort of come up here and talk about that from the other data sets. Let's do that just real quickly here. So this we have 10 values here for each. The median here is going to be the average of those two. When we have an an even number of data sets like that, we do not include this stuff in the middle here. So this part right here gives us the lower half of the data, and likewise here, and there are 5 numbers here, so likewise down here. So the difference there is going to be our 10, and top half here. Actually, rather, this is the lower half of the data, and the upper half of the data is below that. And so when we take a look at the IQR for B, we get 85 minus 27, which is, 85 minus 58, which is our 27 value for the IQR. All right, so hopefully that went pretty well for you. And so today we're going to talk a little bit about standard deviation, and depending on the math that you've taken before, you may have a little bit of exposure to this. You may know a little bit about what standard deviation means. You might even a little bit know about how to calculate it. We certainly looked at it when we did the 1.3 calculator intro activity. We're going to talk a little bit about what it means and how to calculate it by hand. We will not be doing a ton of calculations like these by hand, but I always think that it's helpful to just take a look at one of them just to get a sense of what's actually working here. So, I have a table here that you can see, and we have data values listed in one column of the table, and then a couple other columns to work here. And so our data value here is, this x sub I, each of these, sort of go down this way. First thing we want to calculate is, what is the deviation? And this is something that we actually used, a form of an equation that we used when we were doing the dog blocking activity. Now our average for this one, you may recall, we did that calculation from before, and I think it's also listed up there at the top. The average for this is 71.5. So what we want to figure out is how much does each individual data point deviate from that average according to this formula. So in this case, we're going to take the individual value, 65. We're going to subtract away from it the average, and so this particular data point has a deviation of negative 6.5. If we were to do that with 66, we'd have this. And so on and so forth. So, so those are the individual deviations. And you know, this is pretty tedious calculations. So I'm just going to go ahead and write these out for us. This does not take a whole lot to figure out unless you lose your place here, like I did. 0.1, 0.5, 1.5, 2.5, and then we have three values that are the same. Have a deviation of positive 5.5. Positive deviations means the numbers are above average, and negative deviations are meaning that they're below. You know, one of the interesting things about the deviations is if I were to add all those together, they actually add to be, you know, 0. We should have just as much above deviation above average as below average. Remember that the mean is a balance point, and that's kind of can come through in those numbers. That mean, you know, we have exactly as much stuff above average as below average, and so we added all those up, it would be 0. This next column, we have squared deviations, and squared deviations are quite literally just taking these values and squaring them. And so if I took negative 6.5 and I squared it, I get 42.25. If I took negative 5.5, I'd actually get 30.25, and so on and so forth. We'll kind of skip ahead here a little bit. But, you know, I guess part of the reason why the standard deviation works the way that it does, let's take a step backwards here a little bit, is that when I add all these numbers together down here, I actually get 0. So I can't really use that number by itself as a measure of the spread, because that's always going to happen no matter what data set that I have. So what I want to do, and of course it's happening because the negatives and positives are canceling each other out. So what I'd like to do is to try to get rid of that. And I guess part of that is, part of the reason why we square there is that it then turns all these negative numbers at the first part of the data set here into positive numbers when we square them. So I'm going to go sort of jump ahead here to what this table looks like when it's completed. Won't bore you with the tedious calculation there, but this is kind of what it looks like completed. Remember that the sum of the deviations was 0, but the sum of these is actually where we start with calculating that standard deviation. If I add all those together, I actually get 204.50. That is the sum of the squared deviations. Now what we want to do with it beyond that is we're going to take that number, 204.50, whatever that sum actually is, goes here, and we're going to divide it by n minus 1. And n minus 1 is just the number of data points, or rather n is just the number of data points, and we're going to subtract 1 away from that. And that, at least initially, might seem counterintuitive as to why I want to do that. We will talk a little bit about why that is and how it makes sense that we do minus 1 instead of just dividing by n. But for right now, let's just leave it at this. Okay, so we're going to divide that sum by 9 in this case, 10 minus 1. And so when we do that, we actually get 22.72. Okay, now this by itself is a really important statistic called the variance. Oh no, what's happening? I don't have a red marker for some reason. Maybe we'll try green. Green marker also not working. Okay. Oh no. What in the world? For some reason my markers are not working all of a sudden. Sorry about that. Maybe we're back here. A momentary tech glitch. Oh, there it is. Oh, and lots and lots and lots of blue. Let's see if I can get. There we go. Get it to work in red. Okay, so here's the idea. So I have this this number 22.72. This is a really important statistic called the variance, and the variance is really important in a mathematical sort of way. We'll see that later in the year, that the variance plays a really important part in how we combine variables together once we get a little bit more of a foundation put in place. For right now, what we want to just sort of remember about variance is that the square root of it is equal to the standard deviation. So big concept here is that our standard deviation is the square root of the variance. Sorry. And variance has a really specific meaning in statistics, different from variability. We talk about variability and variation in sampling theory and all that kind of thing that we talked about in the last chapter. But variance has a really very specific meaning again. And so if we're trying to still get back to figuring out our standard deviation, so in this case, then we would just take the square root of the variance that we calculated up above. And so when we do that, we end up with about 4.77. And the notation that we use for that is a lowercase s. You may have noticed on your calculator, we did that activity the other day, or we were working with those male-female GPA distributions, that there was an S in the calculator. Sometimes we use a lowercase x just to denote a variable name there. Usually we use x for that. But that standard deviation is lowercase s. We don't want to get that confused with the sigma that's there. Something that we'll talk about again a little bit more later in the year. So the standard deviation of this thing is 4.77. And what we want to think about a little bit is, okay, fine, that's 4.77, but really the question that we need to answer here is, what does that really tell us about the spread of the data set itself? And so when we go about doing that, then here's our interpretation. Okay, I'm going to get used to writing interpretations of this. This is something that we'll see in lots of places throughout the year. What is the interpretation of that number, 4.77? So we'll say something like this: on average, the students scores vary by about 4.77 from the class mean. Of 71.5. On average, the students' scores vary by about 4.77 from the class mean of 71.5. And so this gives us some sense of an average deviation or an average distance of the points to the mean of the set. In this case, about 4.77 away from the class mean of 71.5, which does kind of go to talk a little bit about the original numbers that we started with. There's not a lot of variability there. Where our lowest number is 65, the highest number is 77. That's a range of only 12. There's not a lot of variability in that data set, but on average, those points are about. And again, it's not perfectly that way, but it's roughly the average distance to the mean, the average distance of all the points to the mean. Okay, so let's see here. So if you take a look at the next slide, what we would like to just kind of think about conceptually here is what happens to the following measures if one of the scores. I'm going to back up just a second here. I have one more question here that I want you to think about here real quick. If I were to look at the standard deviation of this data set, this one had a standard deviation of 4.77. The question here is, would this data set actually have a higher standard deviation or a lower standard deviation? Okay, so take a second to think about that, and we'll come back in a sec. All right, so hopefully you decided that you would have a higher standard deviation because the general variability here, even though the average is the same, the average is still right here at 71.5. There's a lot more variability in the data set, and so those deviations, the individual deviations of the points, are, those points are much further away from 71.5 than what they were in the group A data. So you should have a much higher standard deviation for that. And for right now, that's all we really need to think about, just kind of having a good conceptual understanding of what that standard deviation means. Okay, so back to this. Conceptually, also what I'd like you to think about is what happens to the following measures if one of the scores in the group A data increases from 77 to 97. Right, so if I go back to this data, and instead of having this guy here, let's just say it's 97 instead. Let's say somebody just knocked it out of the park and broke the trend here of this class and really got an A in that class despite all the other ones still having their kind of mediocre grades there. Think about then the answer to this question. If I increase from 77 to 97, what's going to be the effect of the mean? What's going to be the effect of the range? Median, IQR, standard deviation. So take a second just to think about that real quick. You can just write increase, decrease, no change, but I want you to think about that. And if you're working with somebody next to you, that's fine. Go ahead and just have a conversation about that real quick. Press pause on the video, and then we'll come back and kind of talk about these a little bit. Okay, so hopefully you had a chance to think about that a little bit. We have this idea of increasing a single value. And so when I look at that and I kind of think about what's going to happen there, hopefully you figured out that the mean is going to increase. The mean increases because the overall sum of all the numbers is going to increase. I'm still dividing by 10, but when I physically go in there and add those numbers up, I'm going to have a larger average than what I did before. In fact, this one is actually going to increase to 73.5. There was an increase in the sum of 20 from 77 to 97. So that 20 divided by the 10 values that are there just gives us an increase of 2 from 71.5 to 73.5. The median will have no effect at all, whether it's one of the largest three numbers or it increases significantly. It's really not really going to have an effect on the median itself. Median will have no change. The range, of course, will increase. That will increase by 20. We're just moving that one value up. The IQR, what do you think about the IQR? That is not going to change at all because those middle data points are not changing at all. It's just one of the extreme values, of larger values. It's becoming extreme. That doesn't affect the middle 50% of the data. So the IQR will have no change. And standard deviation would definitely increase because we're using the mean in the calculation of the standard deviation. And so what we kind of end up with there is a really huge deviation for that value of 97 that wasn't there before. And so it's going to increase that overall sum of the squared deviations. It would increase the variance and, of course, would increase the standard deviation. In fact, this one, if I do this, actually increases the standard deviation to 9.37. I just did that in my calculator before I started recording the video, which is almost, it's an increase of actually over double. We went from 4.77 to 9.37 simply by increasing that one value. So it has a pretty profound impact on the overall summary statistic of standard deviation. Okay, so the big idea here with this in particular is that we see that both the mean and the standard deviation, and really the range, increases as well by 20. That all of those are really susceptible to extreme values. All we did is we took one value of the data set, we increased it by a lot, but that had a really profound impact on the mean, and it didn't impact the median at all. It had a really large impact on the standard deviation and the range, but the IQR stayed the same, okay? And so well, that kind of leads us to our punchline here for the day and for the chapter, this particular section of the chapter 1. So when we describe distributions, there are different ways to describe the center and the spread. This gets back to our cuss and BS stuff, right? And it really depends on the shape of the distribution. So if our shapes, if the shape of the distribution is symmetric, and then what we want to use is x bar, which is the mean, and s for standard deviation. Okay, and that's because you know, those are better summary statistics when I have symmetric data. Average is easy to understand. People who understand statistics have a good understanding of what standard deviation means. And so we're just going to use those traditional measures to describe the center and the spread. So let me write that up here. This goes for the center, and this one goes for the spread. If the data are skewed or if there are outliers, what we saw by moving that one extreme point from 77 to 97 was that the mean and the standard deviation then became disproportionately out of whack with that one, right? So no longer does the mean and the standard deviation, no longer do those actually describe the center and the spread. They've been really impacted by that one outlier in this case. Okay, but the median and the IQR, those have not really changed at all, right? And so what we would use there is a median to describe the center, and we would just use the interquartile range to describe the spread. Okay, IQR quantifies the variability that we actually have in that middle 50% of the data. Okay, and so that's really important to make sure that we're doing that. And if we're comparing distributions, really important here, if one is skewed and one is pretty symmetric or mound shaped, something like that, then the idea there is that we would want to use the median and the IQR, because what we don't want to do is end up, you know, saying, well, this one distribution has a mean of this and the other distribution has a median of this. You can't really compare those means and medians. Same with standard deviations and IQR. So to make sure we're comparing apples to apples, we kind of default to this. So if one of the data sets is skewed or there are outliers in that data set, then we want to make sure we describe the center with the median and the standard deviation with, the spread with the IQR. Okay, so last thing here. So to conclude here, this is the kind of wrapping all this thing up here. So when we describe / compare distributions, we want to make sure the first step of this is just to graph the data. And so we kind of talked about all the possibilities there. We have histograms, we have box plots, stem plots, all those things we talked about. And we have dot plots too. I don't want to forget that one. Okay, so a lot of different ways that we can graph. Again, this is for quantitative data. We have a lot of different ways that we can graph quantitative data. But the first step is just to graph it and kind of see what it looks like. So based on the shape, so we use that graph to figure out what the shape of the data is. And so we, depending on the shape, choose our best measures for center and spread. Okay, and those, of course, are what we just kind of talked about up here. Whether it be again, whether it be skewed or more symmetric, then we want to choose the correct one there. And again, if one of them is skewed, then we automatically want to go towards this guy right here. So we can make a fair comparison and use the same statistics in that comparison. And then the very last thing, everybody's favorite part, is we're going to cuss and BS our way through the rest of that comparison. Okay, so we want to make a good overall statement. You know, remember, we're trying to tell a story about the data. So, you know, what's your first impression of the data? And once you kind of get that overall, maybe that thesis statement, then you want to make sure you kind of go through your checklist of, well, here's the center, here's the spread, here's the shape. Again, that unusual features idea is if there are outliers, if there are clusters, if there are big gaps in the data, then say so. Unusual features is an optional one. There are some distributions, like when we looked at the age of first-time mothers distributions the other day, there were no outliers for that, and there were no unusual features. They were, one was very typically right skewed, one was bimodal, but there really weren't any unusual features. So that one is really optional. If there's nothing to talk about, then you don't need to talk about it. But if there are outliers, then you definitely want to make that mention, and you always, no matter what, always want to define the center, the shape, and the spread. Okay, so that's that. So again, if you have any questions on that, make sure you jot them down on the side of your paper, and we'll talk about these during our next class when I come back. So for now, what I'd like for you to do is to start working on that dissolved oxygen worksheet. So that worksheet was actually created. I went to an AP conference for just AP stats, and actually AP environmental science teachers, and we collaborated on collecting data, analyzing it. So that was actually a data set that we collected. So make sure you read that. There's some interesting points on, particularly on the back, some interesting points about kind of how that all went down, and some errors in the data collection that things like that happen. So do that. That's part of the homework. Make sure you also get to for over the weekend. Make sure you also get to this page 72 homework. We will. I guess that's probably it. So make sure you get those done. We'll review during our next class and prepare for that quiz the following day. So thanks, and I hope you enjoyed the video.